In this video, I'm going to go through the calculations that you need to make to measure the quantum efficiency of a telescope plus CCD system. So let us start with the definition of quantum efficiency, which we'll call Q. This is the number of electrons that are recorded by the CCD divided by the number of photons incident on it. So number of electrons divided by number of photons. So let's start with the number of electrons. Right? Remember that this is proportional to the number that comes off of the CCD, but is not equal to it. And the proportionality constant is this thing we call the gain. So this is the gain times the count, and it's that count that's in those funky units of ADU, or analog digital units. We measure the gain from those pairs of flats. It was the slope of the plot of variance against flux in pairs of flats taken with the same length of time and the same illumination. And so you can measure that separately, but let's assume we just know it right now. Okay, now we need to work out the number of photons. And this obviously depends on what you're observing. What we're going to do is do the number of photons that hit the CCD from a star of a known flux. Okay, so let's start by considering the flux from a star at a fixed frequency. So we'll call this F nu. So this is going to have units, or the SI units of this will be watts per meter squared per hertz. To get the total flux from the star, you need to integrate over the frequency. So if you have our sort of typical black body spectrum, right? This is frequency, and this is the flux as a function of frequency, and this would be, what's arriving at the top of the atmosphere, at the top of the Earth's atmosphere. To get the flux in a given range of wavelengths, you just need to sum up the flux across the range of frequencies, range of wavelengths, this equivalent, right? So this unit, or a very small fraction of this unit gets called a Jansky. So recall that 1 Jansky, or 1 GAY, is, let's get the number right, 10 to the minus 26 watts per meter squared per hertz. So it's a unit of flux density. That's the SI units. If you prefer CGS units, this is the same as 10 to the minus 23 ergs per centimeter squared per hertz. Okay, so now we want to convert the energy flux into a photon number flux. And we remember that the energy of a single photon is related to the frequency of that photon by the Planck constant h nu. So the number of photons of a given frequency that come from a star that has a certain flux at that frequency is just n as a function of frequency equal to the flux divided by h nu. Okay, so far so good. So now we just care about one frequency though, right? So we have to sum over all of the frequencies. So our n tot that comes in 1 second is going to be the integral over the band of the number at a specific frequency over all of the frequencies. Okay, however, we have to account for the atmosphere transmission. Oops, that's not how you spell atmosphere. Atmosphere. And the filter transmission. So if we add our little sketch again, so we have, the shape that the star is emitting, but then we have a certain filter transmission. And so we have to do this complex integral over some effective widths of the filter in order to get the number we need. So if we want to write it mathematically, you'd write that the total number of photons per second per meter squared will be this integral over the band that you're considering of the atmospheric transmission as a function of frequency. So this is your atmosphere. And then you'd have some kind of telescope transmission as a function of frequency. So this would be the filter, plus any glass or anything else that's going on, any dust. Then you would have your energy so then you would have your total number of photons. So your n nu, remember n nu was equal to f nu over h nu. So the number at a specific frequency. And then you would, well, in fact, let's write that as, let's write that as f nu divided by h nu, and then you'd have a d nu just to do that sum. And so this would be in photons per meter squared per second squared. Okay, so if you want to see Ryden and Peterson's take of this, this is equation 6.25 in Ryden and Peterson. That's on page 164. They do it for a constant atmosphere transmission, a constant filter transmission over a given filter. So we have this table. Go back to the last slide, right? We have here d nu over nu, this term here. So we're just going to replace that with d lambda over lambda of numbers that was in the CCD lecture notes, and that gave you this thing called d lambda over lambda for each filter. So you can find that table and look at those different numbers. So why are they using d lambda over lambda? And I've done it in frequency. Remember that frequency for light is the speed of light divided by the wavelength. So if we do d frequency by d lambda, we can all do that. We get minus c over lambda squared d lambda. If we put back in for frequency c over lambda, this becomes minus the frequency d lambda. So, minus frequency over lambda d lambda. That's important, right? Not d lambda. Okay, it's a fantastic video. Anyway, so it's going to be minus nu over lambda, like that. Let's not confuse you with these stuff. Okay, so now I think we're all at the point where you can be happy. So this is d nu over d lambda. So we can rearrange this and we can find out that d nu over nu is the same as d lambda over lambda. Okay? So the total number of photons coming in 1 second is some kind of average flux in your band times this slightly complicated integral. T nu d lambda over lambda, which is the same as d nu over nu divided by h. And so what they've gone and done in that table is give you this. They're telling you that this ends up being 1.51 times 10 to the 7 photons per second per meter squared per Jansky. And then they give you this value, d lambda over lambda, for each band, because it's going to be different in the different bands, right? And so basically there is a constant times this funky shape that they've calculated. And this is the flux in the table if you're dealing with an m equals 0 star. Okay. The other complication is that it's the number of photons per second per meter squared. So if you've got a telescope with an aperture that's not a meter squared, so a telescope of aperture A, the number of photons is going to be the flux in your band in Janskis times 1.51 times 10 to the 7 times d lambda over lambda for your band times the area of your telescope, and that's going to be the number of photons per second. Okay. We need to look up the flux in the band for an m equals 0 star, correct it to the magnitude of the star we're actually observing, multiply it by 1.51 times 10 to the 7, d lambda over lambda, which is in the band, and the area of our telescope. And so this is the area of the telescope. It's got nothing to do with the CCD, but this quantum efficiency you're calculating does depend on the size of the telescope a little bit. So let's say, recall, for a telescope of diameter d, and it's usually the diameter that's reported. For example, ours is 16-inch diameter telescope. The area is just pi d squared over 4. And be careful with units here. Okay, so that's all we need to do. So let's go ahead and do it. So I observed Spica, which has a V-band magnitude of 0.97 usually. Turns out it's a variable star, so not a great one to use for calibration, but that's the one I used. In my 0.1 second observation, I recorded 1.04 times 10 to the 7 ADU. That means in 1 second, I get 1.04 times 10 to the 8 ADU. Whoops. That's not ADU. Well, anyway. Sorry. ADU. Okay. Let's use a gain of 1 over 0.6. Turns out that's pretty much what I measured, so 1.67. So that means that my observations of Spica released a number of electrons in 1 second. That was 1.7 times 10 to the 8. So this is electrons per second. So now I need to calculate the number of photons per second. Okay, so this is V-band. So that table tells me that for an m equals 0 star, the V-band flux in Janskis is going to be 3640 Janskis. And the d lambda over lambda factor I need to account for band transmission and atmospheric transmission is 0.16. Okay, so now I need to convert this flux to the flux for my star Spica, which has a V-band magnitude of 0.97. So we have to use one of these magnitude equations. We use this one, m1 minus m2. It's 2.5 times the log of the flux ratio. Okay, so we're going to do F1 as 3640 Janskis, M1 equal to 0, M2 equal to 0.97, and F2 is what I want to find out. So if we put that all into the equation, we get minus 0.97 is 2.5 log F2 divided by 3640 Janskis. Rearrange it, and we get F2 ends up being equal to 10 to the minus 0.97 over 2.5 times 3640 Janskis. I always like to do this step at a time. So this ends up being 0.41 times 3640 Janskis, or otherwise known as 1490 Janskis. I did all these numbers in advance. I'm not that quick. So I like to do it longhand, because then I sit and I'm like, okay, so it's smaller flux, larger magnitude. Yes, that makes sense because magnitudes are backwards. So it's a smaller flux than a magnitude 0 star. Almost everything will be smaller because magnitude 0 stars are the brightest stars in the sky. Okay, so now we've got our flux. So then let's calculate the number of photons per second. And that's going to be equal to this flux. So 1490 Janskis times our 1.51 times 10 to the 7 factor times our d lambda over lambda, which this we'd worked out was 0.16, times our area squared. So let's calculate the area. So the diameter is 16 inches, which ends up being 0.406 meters. area is pi d squared over 4, ends up being 0.13 meters squared. Okay, so the number of photons per second equals 1490 times 1.51 times 10 to the 7 times 0.16 times 0.13. And you do all those sums, you end up with a number of 4.7 times 10 to the 8 photons per second. So finally, we can calculate our quantum efficiency, which is the number of electrons divided by the number of photons. We've done both of them in a second, so we have the right thing. That's another thing that can go wrong, not doing it in a second for each of them. But from my calculations, this is 1.7 times 10 to the 8 electrons per second divided by 4.7 times 10 to the 8 photons per second, which ends up being 0.36. So I end up with a 36% quantum efficiency in V-band through our telescope onto this CCD. So this is lower than what's reported by FLI for the CCD, because that's just the direct, like if you have the number of photons directly hitting the CCD. So this isn't just the quantum efficiency of the CCD, it's the CCD on our system under the atmosphere that that I was under when I took this data, which will be slightly different to yours, right? Because I did this in the summer and you have been doing this probably in slightly better weather. Okay, so hopefully that helped, and good luck calculating your own quantum efficiencies.